Hello students, welcome to the physics session. In today's session, we will be discussing about applications of Biot-Savart law. Applications of Biot-Savart law, especially magnetic field due to current carrying conductor, straight current carrying conductor and circular current carrying conductor. And we'll work out few special cases related to these as well. Okay, so let us meet at 8:30. Right. Right, okay, everyone. So, moving charges and magnetism. Project please. Right, very good. Guys, come this side. You guys are sitting there. That's it. Come here. Come here. The last row, both of you also come here. Right. Yes. Come. Right, okay. So I hope for the online students are getting properly. If there is any issue with the voice clarity or anything, you can ping me a message. Drop me a message. Right. So in the previous session, we have discussed about what is that? Biot-Savart law and one of its application, especially how to find the magnetic field due to straight current carrying conductor. Now let us see. Let us try to recollect back briefly. Let's try to recollect that back briefly. Then we'll go ahead with another application, that is how to find magnetic field due to circular current carrying conductor. Okay, right. So Biot-Savart law. Yes. What is the mathematical expression for Biot-Savart law? Magnetic field due to a small current carrying element dB is equal to mu naught by 4 pi into I dl. Can you switch off all the fans once? Switch off all the fans. This fans will switch off. All the fans. I want the class to be pin drop silent first. Right, very good. Yes, very good. Switch off everything. No mosquitoes, no problem. Right. First, be quiet, everyone, and note down every point. It's not time pass. If you are not interested, you can go. No problem. But it's we have very less time. Keep that in mind. Hardly you don't have even 1 month, 2 months time. If you can't recollect back and practice, simply you are taking like this a time pass. Then you will practice. Is one of the very important chapters I told already. Keep that in mind and note down every point and practice. So, Biot-Savart law, mathematical expression. Actually, the statement says that the magnetic field due to a small current carrying conductor of length dl at a point P, which is at a distance r, is directly proportional to current in the conductor I and length of the conductor and sine of the angle between the current and the line joining the point and the element, and inversely proportional to square of the distance between them, between the element and the point. Okay, so it is ideal sin theta by r square. Ideal sin theta by r square, right? So vectorially, you can write it as vector. The vector form of it is given by dB vector is equal to mu naught by 4 pi into I into dl vector cross r cap by r square, you can write, or dl vector cross r vector by r cube, you can write, because r cap can be expressed as r vector by r, right? This is the what you call vector form of Biot-Savart law. Vector form of Biot-Savart law. This is the magnetic field due to small current carrying element. Whereas the total field due to the entire conductor is given by integral of dB. Integral of dB. We take this concept out and integrate the remaining factors. You'll get the total field. By you making use of this or this law, we have already discussed how to find the magnetic field due to a straight current carrying conductor, finite straight current carrying conductor, or thin current carrying conductor specifically. If the current is very thick, then field will change because current will distribute uniformly, right? Then the field will change. So if you consider a straight current carrying conductor, a thin and straight current carrying conductor, due to this at a point P, which is at a perpendicular distance D, we are asked to find magnetic field. Already we have discussed. If the line drawn from the top end to the point makes an angle alpha with the perpendicular line and the bottom point, if you draw a line from the point to the bottom point, if this line is making an angle beta, so you have to consider what you call the orientation of the angle. Actually, here from the perpendicular line we are measuring the angle. The alpha is measuring in clockwise direction, beta we are measuring in anti-clockwise direction. Now, by taking the proper limits, first if we consider a small element dy at a distance of y from here, and if we draw a line here, and by considering symmetrical relations, if you integrate, if you will get a dB small magnetic field, and hence on integrating this, you will get a total magnetic field. That total magnetic field is due to the straight current carrying conductor is nothing but what? Mu naught by 4 pi d. Mu naught I by 4 pi d into sine alpha plus sine beta. Right? This is actually small field you have to get, then by integrating this, you will get this one, the final expression. Here you have to remember that this angle should be measured with respect to alpha and beta. By taking this into consideration, we have also discussed about infinite conductor, how to find magnetic field due to infinite conductor and semi-infinite conductor, right? So this general form I have to remember. And one more thing, you may be given in the question, instead of this angle is also may be given. If these angles are given as something like theta 1, theta 2, or even this are given as alpha, beta, you have to consider, if say for example now if you consider this is theta 1, this is theta 2, this will be 90. In terms of alpha, beta, I can express it as 90 minus alpha, this will be 90 minus beta. So then you will get in cos terms. So sine of 90 minus, if it is in terms of this, we are expressing, then you will get the cosine terms. Is it clear? Or if this is theta 1, you can take alpha is equal to 90 minus theta 1. So sin 90 minus theta 1 should be cos theta 1. Similarly, this will be cos theta 2. So you'll get in terms of cosine functions. That you have to remember. I'm not giving it here. Okay. And the applications. Quickly, let us recollect back two more points. That is another special case or infinite conductor. If you have a conductor which is going to infinity, it is going to infinity. Then due to this, at a point P, which is at a perpendicular distance D, we are asked to find magnetic field. So we have to consider that this line, the line which we have considered, it will go to the infinity, and so it will be looks like parallel to this conductor. So alpha is equal to 90 degrees or pi by 2 radian, and this line also looks like parallel. So beta is also equal to 90 degrees or parallel. And if you substitute these angles there, you get what is this? B is equal to mu naught I by 4 pi d into sin 90 plus sin 90. 1 plus 1, 2. So we'll get mu naught I by 2 pi d will be the magnetic field due to infinite current carrying conductor. Infinite thin current carrying conductor. Right, whereas the another one, semi-infinite conductor, or the magnetic field near one end of a current carrying conductor is given by. So if this is there is a conductor, it is going to infinity. That is redraw once again here. This general formula you have to remember. Semi-infinite conductor. If this is a conductor, it is going to infinity. This end is near you, near your hand. So near to one of the end, if you consider a point which is at a distance d, in this if a current I is passing and it is going to infinity, this is at your end. So this is going to infinity. In that case, this line drawn will be looks like parallel. So and hence alpha will be 90 degrees, but beta will be parallel to this. So beta will be equal to 0 degrees. So and hence, as B is equal to mu naught I by 4 pi d into sin alpha plus sin beta. So here alpha is 90, beta is 0. So what do you get? 1 plus 0 is 1. So here B is equal to mu naught I by 4 pi d. Yes? Copy. And I have given one question. Let's discuss that. Then we'll discuss a few more examples based on this. And then we'll discuss another application. That question which I have given you, try to add one more point to that, and let me give you that question clearly once now. The question is, if you have an infinite conductor, if you bend the conductor in such a way that this is going to infinity and this part is going to infinity, so actually this infinite conductor have bent like this. So that angle here, current is coming and going like this. Okay, and I have forgot to mention the angle between them. Let us consider the angle between them is alpha. Angle between these conductors is alpha. We are asked to find magnetic field at a point P, which is along the line, which is this point is bisecting the angle. You can say it is an angular bisector. If you draw a line this, the point is here. The point is at a distance A along the angular bisector. That you have to copy. This distance is given. Distance of the point from this point. What do you call? This is the angular bisector is given as A. So what is the magnetic field? Total magnetic field due to this at this point. It is infinite conductor, but not straight infinite conductor. It is bended in this form. In such case, what would be the total magnetic field here? In such case, what you have to consider is, you should know here this conductor from here to here you have to consider this as one conductor, and this from here to here you have to consider this as another conductor, semi-infinite conductor. This is one semi-infinite conductor, this is another semi-infinite conductor. Due to this semi-infinite conductor, you have to find what is magnetic field here. So what you have to do is, from the point, just like that, if they are asked to find magnetic field at any point, from the point you have to draw a perpendicular line onto the conductor. You have to draw a perpendicular line onto the conductor, and that distance we have considered as D, the formula. So what is this D? A is given here. This angle between these two conductors is given. It is mentioned, and it is mentioned that the point is on angular bisecting line. So that means this angle should be exactly half of it. That means you can take this angle as alpha by 2. Is it clear? It is bisecting means it is dividing equally. Bisecting means bisecting means divides two parts equal. So this is alpha by 2, and this also will be alpha by 2. So this is alpha by 2. You can say this A makes as this is making an angle alpha by 2 with respect to this. So you can write it as this. If you resolve this, you get A cos alpha by 2 will be this. This will be A sin alpha by 2. So your D will be A sin alpha by 2. Is this part clear, everyone? This is the perpendicular distance. In place of D, you have to keep A sin alpha by 2. Similarly, you have to draw a perpendicular line onto this conductor. This is A, this will be A cos alpha by 2. This also will be This is also D is equal to A sine alpha by 2. Got it? So first let us consider this conductor. First semi-infinite conductor. Due to this, what is the field here? So B1, let us say. B is equal to B due to first one plus B due to second one. What is B1 here? B1 as this angle. It is mu naught I by 4 pi D. D is A sin alpha. A sin alpha by 2. Okay. Into sin alpha plus sin beta. Here alpha is, in that case, angle made by the line joining from the top end to the point. Beta is angle made by the line joining from bottom end to the point with respect to the perpendicular. Here this you can see, you can consider this is top end, this is bottom end. This will be alpha by 2. Angle, no, this is alpha by 2. This is alpha by 2, right? So usually angle made by this line with respect to the perpendicular line. This is alpha by 2. What should be this one? This is 90. This will be 90 minus alpha by 2. If you are following, then only you can understand. Otherwise, you'll just feel it is a very clumsy thing. Okay. So this will be 90 minus alpha by 2. So, and here, as it is going to infinity, this line will be parallel. So beta will be 90. So if you consider this one here, sine in place of alpha, 9 sine 90 minus alpha by 2 into what is this? Sine plus beta is 90. So sine 90. So we'll get sine 90 is 1. So this will be cos alpha by 2. So 1 plus cos alpha by 2 is 8. Is it clear, everyone? So to take this as B1, similarly B2 you have to take for this. And substitute, you'll get B. Yes, note down this. Note it down fast. It's finished. I'll give you few other examples. So before that, let us discuss about the circular conductor. Then we'll discuss few examples, few more examples. Right. So is this done finished? What is sin 90? 1 plus this is cos alpha by 2. So you can write it as finally B1 is equal to mu naught I by 4 pi A sin alpha by 2 into this is 1 plus cos alpha by 2. This is due to this here. Due to this also will be same only. So B2 also will be same. You can write this is therefore B2 is equal to B1 equal to this. Therefore B is equal to B1 plus B2. So 2 into mu naught I by 4 pi A sin alpha by 2 into 1 plus cos alpha by 2. This will be the total field. You can keep it as it is, otherwise if you want you can simplify. 2 you can cancel. Depending on the options you have to simplify. Is it clear, everyone? Right. So this is how you have to work out the questions based on calculation of magnetic field due to straight current carrying conductor, maybe infinite conductor, semi-infinite conductor, and at different points. Based on this, we need to have an idea of one more kind of question. That is, if at all, say, let us do one more example. Based on this, write the question. Find the magnetic field at a point P. Find magnetic field at a point P due to the conductor shown in figure. Due to the conductor shown in figure. So this is actually a finite conductor. In this current I is flowing. And here this is a starting point and ending point of the conductor. But we're asked to find magnetic field somewhere here at a point P, which is at a distance. A from this end, so that this is making an angle of 30 degrees with horizontal. 30 degrees with horizontal. Then, how to find the magnetic field due to this entire conductor there? Right. So, in such case, what you have to do is you have to consider top end and bottom end. So, you have to extend this axis and we have to draw a perpendicular line from the point onto the conductor. From perpendicular line onto the conductor from the point. Now this distance is nothing but our d. So this is given, A is given, this is not given, but A is making an angle theta with perpendicular line. So you can take this as A cos 30, A sin 30. This is A cos 30 is D. So you can take this as A cos 30. What is cos 30 value? Root 3 by 2. So it is root 3 A by 2 is D. Right? D. Then what is alpha and what is beta? Alpha is angle made by the line drawn from the top end to the point. Top end with respect to the perpendicular line at the point. So this total angle is nothing but alpha. Right? So here, what is this? So here, if to make it simplified, so this you can take it as little simplified. You can take this as semi-infinite conductor. So this time we're trying to make this a little simplified. Otherwise, you have to give some other. You need to get another data. It is semi-infinite wire, means it is going to infinity here. So this line will be parallel. So this alpha here will be 90 degrees. Alpha is how much? 90 degrees. Then what is beta? Beta is angle between line drawn from bottom end with respect to the perpendicular. This is perpendicular. This is bottom line drawn from bottom end. This is nothing but 30. This is nothing but 30. Got it? Yes or no? So beta is 30 degrees. But we know with respect to this, if you draw two lines, alpha should be angle measured in clockwise, beta should be angle measured in anti-clockwise. Then you have got sign of alpha plus beta. But here, with respect to this, both angles we are measuring in clockwise only. Alpha clockwise, okay, positive. But if beta is take clockwise, you have to take this negative. That you have to keep in minus 30. In such case, if you substitute all these values, you will get B is equal to mu naught I by 4 pi D into sin alpha 90. Sin 90 is 1 plus sin beta minus 30. So sin of minus theta is minus theta. So minus sin theta. So you can write it as minus sin 30 is 1 by 2. So 1 minus 1 by 2 is 1 by 2 only. So we'll get is equal to what? Mu naught I by 8 pi D will be the value. Got it? So this is how you have to work out this kind of questions. Right? These are a few very important method of questions usually have asked in previous years in different exams. Right? Now let us see another application of Biot-Savart law, that is how to find magnetic field. First, let us see at the center of a circular current carrying conductor. Then, at any point on the axis, if you consider circular current carrying conductor on the axis at any point, how to find what is that formula is. Okay. First, write down next application. What is that? Magnetic field at the center of circular current carrying conductor. Write down. Magnetic field. Second application. Field at the center of magnetic field at the center of circular current carrying conductor. Current carrying conductor. Magnetic field at the center of circular current carrying conductor. Right. How to find this? So by using Biot-Savart law only. So let us consider there is circular current carrying conductor having radius R. In this, current I is flowing in, let us say, in anti-clockwise direction. Current I is flowing. Are you following, everyone? So let us consider a small element of length dl. Due to this small element, what is the field at the center O? If you find, then if you integrate throughout circumference, so according to Biot-Savart law, the small field produced due to the small element is what? Ideal sin theta by what? Mu naught by 4 pi into the constant is equal to mu naught by 4 pi into ideal sin theta by r square. Yes, where I is the current passing through this, in this current I. dl is length of this element. Okay. Theta is angle between dl vector, that is the current direction, and a line drawn from the element to the point, this one. So usually this element, this is the current element, and this will be perpendicular always. So angle between them should be 90. In this case, it is 90. So sin 90 here, because theta is equal to 90, you can take sin 90 is 1. Okay. So directly you can take dB is equal to mu naught by 4 pi, or mu naught I dl, or mu naught I by 4 pi r square into what? dl. Got it? Here R is what? Distance of the point, that is capital R. You can take capital R only. Capital R square. This is fixed. Right? Now, the total field at the center due to the circle, if you want, B is equal to integral of dB is equal to mu naught I. Mu naught by 4 pi is constant, I is also constant, R is also constant. If you take this all out, you can write mu naught I by 4 pi R square into integral of dl. dl, the small element, if you are increasing the length of this element, it goes from here to here back. What is the total length? Circumference. So it goes from 0 to 2 pi capital R. So integral of dl is L. Substitute this, we'll get into 2 pi R. And simplifying further, we'll get B at the center of a circular loop is mu naught. What is this? Mu naught I by 4 pi R square into 2 pi R. 2 pi 2 times. And 1 R gets cancelled. So 2R. Mu naught I by 2R. Is it clear? So magnetic field at the center of a circular loop is B is equal to mu naught I by 2R. Remember this. And I will give you one general formula related to this. To find the magnetic field at the center of any circular, due to any arc of a circle. Due to any arc of a circle, if that arc may be subtending an angle of 360 degrees or 180 degrees or 90 degrees or some angle 30 degrees, whatever it is. How to find that? Let us see one generalized relation. So general formula, right? General relation, general formula for finding magnetic field due to circular current carrying conductor. So if you have in a circular track, let us consider there is an arc of a circle. This is center. This arc is subtending an angle of theta. How much? Theta, which is having a radius of r. So the arc length, let us consider it is total length of the arc is L. What is? If you consider small element dl, due to that field is this much. Due to the dl is this dB. You know, type before by square dl. Due to the arc of length L is how much? Here B is equal to integral of dB is equal to mu naught I by 4 pi r square into integral of dl is L only, but here L is going from here to here. What is the length in terms of the angle and radius is the point. So you know angle equal to arc by radius, and hence you know that angle is equal to, because angle is equal to arc length by radius L by r. So L is equal to r theta. L is equal to r theta. So you can here it is going from 0 to L. Length of this arc is nothing but r theta. L is equal to r theta. Is this clear? The limit. So integral of dl is L. So now if you substitute this, we will get B is equal to mu naught I by 4 pi r square into r theta. Here one r gets cancelled. So you can write it as B is equal to mu naught I by 4 pi r into theta. Is the magnetic field at the center of center due to an arc of a circle, which is subtending an angle of theta. That can be any angle. If it is 2 pi radians to the complete entire circle, what is the angle subtending by the entire circle? 2 pi radians. If this is 2 pi 2 times, so mu naught I by 2r. Mu naught I by 2r. Right? If it is a semicircle, angle subtending will be pi radians. In terms of radians, you have to take pi radians. So semicircle, pi cancel, let mu naught I by 4r. Right? So depending on the angle subtending by the arc, that is a quadrant, semicircle, or full circle, you can find out the field due to the circular arc at the center by using this. This is general formula. Is it clear, everyone? Now, based on this, let us do some examples. And this is one of the very, very important application. Now, let us see some examples. Right. Find magnetic field at O. Find magnetic field at O in the figure. Find magnetic field at O in the figure. We have a simple case I'll give you. There is a semicircular ring in this current I is flowing. This is diameter. So here this is the point A, this is point B. So current is flowing, this is center O and radius R. This is O. What is magnetic field due to the semicircular ring at point O? Yes, from the unit I by 4 pi R into theta is how much? Semicircle. Angle subtending at the center by semicircle is 180 degrees or pi radians. Pi. We substitute that pi, get pi by cancel unit I by 4 R. So what is this? In this case, V is equal to V naught I by 4 pi R into pi. So pi cancel. V is equal to V naught I by 4 R. That's it. Got it? Another example. Same. Find magnetic field at O, at point O, due to the figure shown. Due to the figure shown. Or you can say under the same question, this is the first one, this is second one you can take. So here we have given yes, semi-infinite conductor. That means we have a wire, it is coming from infinity and is ending here. In this current I is flowing. At this end, it is connected to a semicircular current carrying conductor. So, and it stops here. Or you can consider that it is again going to infinity. This is again one more semi-infinite conductor. This is one semi-infinite. This is semicircular. This is semi-infinite state conductor. Due to this is center O and this is radius of the circle. So, what is the total magnetic field at O? What is the total magnetic field at O? You have to remember, I have given you one to note in the previous session that if the point is lying on the axis of the current carrying conductor, alpha equal to 0, beta equal to 0. So, total field will be 0. Let us divide this into three parts. This is first one, this is second, this is third. So, total field at O is equal to B due to the first one, plus B due to the second one, plus B due to the third one. Due to first and third, it is 0. This is 0, this is 0. Due to the third one is this one. So, that directly you can say is mu naught I by 4R. Got it? Yes, everyone? That's it. Right. So, like this, you can consider, you may come across different questions also. Let us see one or two, then I will go ahead with the next point. Right. So, I will wind up in 10 minutes. So, next example. Right. Next example. Right on. Find magnetic field at O. Find magnetic field at O. We have this is a straight current carrying conductor and a semicircular current carrying conductor. This is again a straight conductor. So this current I is going here, is flowing through this and flowing through this. Then again it is connected to another semicircular wire and it is flowing in this direction. Same I. Following or not? This is center O. This is radius of the inner part is R1 and radius of the outer part. Radius of this outer circular part is R2. Is it clear, everyone? So, what is the total field at O? Find total field at O. Find total field at O. So, what you have to do is, here you can divide this into one straight conductor. Let us start from here. 1, 2, 3, 4. 4 conductors are there. So, total field at O is equal to B due to 1 plus B due to 2 plus B due to 3 plus B due to 4. But due to 1, the point is lying on the axis of this. Due to this also lying on the axis. So, due to 1 and 3 is 0. This is 0, this is 0. Yes or no? Whereas about due to 2 and 4, if you observe, you have to remember one more point here. How to find the direction of magnetic field due to straight current carrying conductor or any circular current carrying conductor. You have to use Biot-Savart law. According to this, magnetic field is given by this. But direction is given by right hand thumb rule, or I can say right hand palm rule. Right hand palm rule. If you have a current carrying conductor, let us say this is a current carrying conductor, and this current I is flowing, and at this point P, if you are asked to find what is the direction of magnetic field, if you are asked to find the direction of magnetic field at that point, you have to use right hand palm rule. Right hand palm rule. According to that, you stretch the thumb in the direction of current and stretch the fingers of right hand onto the point. Then the palm is this palm. The direction of palm gives direction of magnetic field. Here, palm is into the plane of the board. So it is into the plane of the board. Is it clear, everyone? If the direction is downward, then you have to stretch the thumb in this direction and you have to stretch the fingers onto the point, then palm will be outward. If the current is down, palm is outward, so magnetic field will be outward. As current is upward, field will be down into the plane. Is it clear, everyone? Right. So according to this, if you stretch the thumb in the direction of current, you have to stretch the thumb in the direction of current. Stretch the thumb in the direction of current and stretch the fingers into the point. What is the direction of palm? In first case, in case of two, second one, the second connector. Into the plane. So B2 will be into the plane. Is it clear? Then due to the fourth conductor, stretch the thumb in the direction of current and stretch fingers onto this. Can you stretch like this? Like this? So, as per your convenience, you have to hold it. That means you have to hold the conductor by stretching the thumb in the direction of current. So, hold it and stretch the thumb in the direction of current. And now stretch the fingers onto the point. So, palm is outward, right? So, field due to this is outward, whereas field due to this is inward, opposite directions. Is it clear? So, net field will be difference between these two fields. So, you can say vectorially, you have to use vector representation for that purpose. Actually speaking. So, 2 will be 2. This is second conductor. This is fourth conductor. 2 will be into, 4 will be outward. Into will be represented with a cross notation. Outward will be represented with a dot notation. So, simply you can say. So, therefore, V naught vector is equal to B2, which is this only magnitude part. If you want to know, magnitude is same. With the direction, if you observe, B2 minus B4 minus B4, only magnitude of the resultant field if you observe. Okay, right. So the larger one minus smaller one. Larger one minus smaller one. Which is larger? According to B here, for a circular, semicircular conductor, this is mu naught I by 4R. If R is small, total value will be large. But R is larger, total value will be small. So for the larger radius, value will be smaller. That is for fourth one. So you can see this is small. Larger minus smaller. So it is equal to mu naught I by 4R1 minus mu naught I by 4R2. Yes? Yes or no? Due to semicircle. So now mu naught I by 4 is constant. Take it out. Then you get mu naught I by 4 into 1 by R1 minus 1 by R2. You can keep this as it is. That's it. Or depending on the options, you have to simplify further. In the options, if it is given as R1, R2 minus R1 by R1, R2, that will be. Or instead of that, the numerical values are given. R1 is 2 centimeters, R2 is 4 centimeters, like that. Then you have to substitute the values and you have to get the numerical value. Okay, right. This is how you have to work out. You have to find the magnetic field due to straight current carrying conductors and circular current carrying conductors and combination of this. Yes, is it clear? Right. Okay. So I'll give you one simple example. Homework. You try yourself. Right. So find magnetic field at O. Find magnetic field at O. We have this is x-axis, this is y-axis. We have a circular. We have circular conductor. This current I is flowing. This is in the plane XY plane. You are following? It is in XY plane. Now this is z-axis. This is z-axis. The conductor is, you see, semi-infinite conductor is connected here along z-axis. In this current I is flowing. This is semi-infinite conductor. And after this again it is going parallel to this. It is again another semi-infinite conductor. It is going here and coming here and crossing this current I. So this is center O and this is the radius R. Got it? Let's find the magnetic field at O is the question. So try this yourself as time up. I'm winding now. Okay. Try to practice few more questions based on this. This concept is very important. In the next session, we'll discuss about the other related concepts. and we'll have to wind up in 2 more sessions. Okay? Yes. Fine. Right. And don't just relax. Again, I am telling. Try to be little serious. You have very less time, and practice yourself at least 5 to 10 questions in each track per day. Okay? Then you will get the confidence by yourself. So if you are like in a free mood, automatically that seriousness will not come. Try to be a little serious and practice yourself. Okay? Okay then. Take care. Bye bye.